Professor Zhang Yuanhan here. It's also an honor for me to introduce him. So I guess probably I know him very well. That's the reason, because Professor Zhang Yuanhan graduated from this department. So he is 1 year senior than me. So at that time, I think I roughly recall Professor Zhang Yuanhan is always among the top 1 or 2 in his class. And also, after the graduation, I think the Nobel laureate same team somehow visit Taiwan, then try to select very talented young people to join his group. So basically, he has hold a test. Then I think Professor Zhang Yuanhan got selected. Then his name went on the newspaper. So that's a big news. So probably I think that's initiate. So this kind of effort, somehow we have create a special channel to let the young people who are interested in physics, somehow they have a special channel to join. That's just for his undergraduate record. But after graduation, I think he joined a simultaneous group. Then again, I think he is very good in electronics, hardware-related things. Because I recall in the so-called simultaneous exam, there is even applied electronics circuit or something like that. That's very amazing. I think so basically, Professor Zhang Yuanhan is like a role model for us. So he set up the tone. So many young guys then try to change, to throw away the pencil, then try to do something in hardware-oriented work. So I think Professor Zhang Yuanhan hold many important posts, also in many big international collaboration, like L3, Phobos, and also CCMS, like the Higgs boson 3. Then also this AMS. So I think let's give him a very big applause, and let's welcome Professor Zhang Yuanhan.
Thank you. Thank you very much. I think Minzu greatly overstates my role. I'm just one of the alumni of this department, and I'm very, very honored to come back here to give this lecture. So today I will report to you the results of our experiment called AMS. This is AMS. It's a spaceborne experiment on top of the International Space Station. This is the living part of International Space Station, and this is a truss which holds all the big components of the space station. Total about 110 meters long and 80 meters wide. So AMS is international collaboration. It consists of about 60 institutes all over the world. The detector itself is mainly constructed by Europeans in this region, and in Taiwan, we construct most of the electronics for this experiment. And then, of course, in the United States, we're responsible for launch the detector into the space station. So it's a big collaboration with about 500 participants. This is AMS in the card view, and you see many detectors in this about 3 meter high and 2 meter wide device. Here I want to give you a very brief introduction of the principle of our detection. From the beginning, we have a magnet. This is a permanent magnet. It is permanent because you don't want to build electromagnet. It will be taking too much power. We tried to build a superconducting magnet. At the end, it was decided that permanent magnet is better for this mission. And this is permanent. This magnet has a special feature that we have magnetic field inside, but no field outside. There's no dipole outside, because if there's a dipole, the dipole will interact with the Earth's magnetic field, and it will turn the International Space Station. So it's not allowed to have any dipole outside, but there's a strong 1 kilogauss field inside. Now, to detect cosmic rays, we put 9 layers of very precise detector, silicon tracker inside. This detector can register where the particle goes through the tracker, and if you connect these points, the interaction points, you get a track. And with this track, you can decide whether it's a positron or an electron, and also we measure the momentum of the particle. Now, this is all fine, but the main problem of the measurement is that in the space, it's not only electron, positron. Actually, 90% of the cosmic rays are protons. Proton to positron is 10 times 4 more proton than positron. So what the biggest challenge for us is to separate this 10 to the 4th of protons from positron. Now, positron and proton has both charge 1, positive 1, so they all bend in the same direction. They look exactly the same in the tracker. And that means we need some other detector to help us to distinguish them. So what we do is first we put a transition radiation detector. This detector uses a material such that the electron, when it goes through this detector, will emit transition radiation. It's a low energy photon. So we detect this photon, and it helps us to separate proton. We can reject about 100 times the proton. That means every 100 proton, you probably get 1 misidentified. Now this is not enough, because as I said, there are 10 times 4, 10,000 more protons than positron. So we have another detector at the bottom here. This is the decal electron. So this is a calorimeter. In the calorimeter, most of the proton just go through or radiate individual particles, but electrons or positrons give the electromagnetic shower. It's a very compact energy in this region. So with this, we can separate electron or positron and proton with a proton rejection about 10 to the 4th. So if we combine these two detected transition radiation and the calorimeter, we get a total rejection of 10 to the 6th, which help us to reduce the background of proton down to a manageable level. So this is how AMS works. Now in detail, some picture of these detectors. This transition radiation detector looks like this. 20 layers of straw tubes with some material in between. This picture shows the tracker. There's 9 layers of tracker, the silicon detectors. And this is the calorimeter at the bottom. It's 18 layers of lead and scintillating fiber. And there are 2 other detectors, time-of-flight detector and Cherenkov detector, here and here. These detectors are less important in this measurement, so I will not go into details. In addition to the detectors, there are a lot of electronics that has to be implemented to read out all the signals. We have a total about 200,000 channels of signal, which have to be read out about 2,000 times every second. So electronics has to be very fast. Now, electronics as well as all the detectors, the biggest problem is that it has to operate for 20 years. And we want to implement the same kind of detector as in the ground experiment, like in the LHC experiment. Now, the problem is there's no maintenance for 20 years. You cannot send an astronaut to repair anything. This electronics in AMS, as soon as it's broken forever. There's no way to recover them. So you want to build the electronics that can last 20 years, survive 20 years. And however, the environment is very bad because in the space there are very strong radiation, there's extreme temperature variations, it's in vacuum, so you have problem to get rid of the heat. We have a lot of vibration during launch, and as I said, there's no maintenance. It doesn't help. So to mitigate these problems, our design, first of all, it has to be redundant 2 times in general. So we have always, for most of the electronic channels, we have 2 sets of identical electronics. If one breaks, you use the other one. For our main CPU board, we have 4 times redundancy. We have to choose radiation-hard components. We'll do a lot of thermal cycling, thermal vacuum test, and vibration test. And that is why, with all this, the experiment took about more than 10 years to construct. It's not a very huge detector, but it really takes time. These are, for example, the electronics board we built. I mention this particularly because all these are designed and produced and space qualified in Taiwan, mostly in CSIST, Zhongshan Institute of Science and Technology, National Space Program Organization, Academia Sinica, and NCU, where I come from. So this is how AMS look like on ground. The detectors are inside with electronics implement on this boards on either side of the detector. These boards are radiators. It radiates the heat. In space, you cannot use air to cool the electronics, so you have to reduce temperature by radiation. All these boards will be painted white to radiate heat, and then electronics, most of heat are produced and are attached directly to this board. So it's on the back side of these boards. It's I think it's most effective in radiating heat. But also it does not absorb heat. Yeah. So after the detector was constructed, we spent a lot of time doing space qualification. One of the most important steps is this thermal vacuum test. The thermal vacuum test was carried out in a huge thermal vacuum chamber. This chamber is very big. It's like this room, the size of this room, but it can be vacuumed completely to 10 to the -9 bar. And the AMS stayed there for 14 days with temperature cycling variations to verify that it works well in space conditions. And also we took about 6 months in the accelerator on ground, use beam particle to calibrate the detector. This is done at CERN, where you see the detector was lying flat, with particle coming from the accelerator. So we took a lot of data with protons, electrons, positrons, and pions to calibrate various detectors, including most important task is for tracker alignment. It's very important to align the tracker to better than few microns precision. We measure the tracker resolution, energy scale of ECAL, the electromagnetic calorimeter performance, TRD performance for electron and positron, proton and electron separation. So after all this was done, in August 26th of 2010, 3 years ago, it was carried by this huge aircraft, C5 transporter from Geneva to United States in Florida, Kennedy Space Center. The biggest normal cargo aircraft Boeing 747 was not big enough to carry, so we have to ask U.S. Air Force to help with this. And these are the astronauts who has already at that time been identified that will take on this mission to space. And in KSC, in Kennedy Space Center, the AMS in October 22, 2010 was mated with a simulator of the space station truss. So there was no problem to connect it to the simulator. And then it was put into the space shuttle. You see, this is the cargo bay of the space shuttle. See the door, the two cover of the cargo bay, and the astronauts stayed in the front region. So this AMS is put here with some other payload in this flight. April 26, 2011, 2 years ago, shuttle cargo bay was closed. The door was closed. See 3 persons down here just to watch, make sure that nothing was stuck behind the door. The door was closed smoothly. And this is almost before the launch. This is our project leader, Professor Samuel Ting, and this is the commander of this shuttle flight, Captain McCarty. He's kind of famous at that time because, not because of he himself, but his wife. His wife was a congresswoman. At that time, was shot by some random firing and shot by head. So it was just 1 month before the mission. He made a hard choice to continue working with us and being the commander of this mission. So this is just a pre-flight preparation. Yeah, of course it is. Yeah. The launch was in May 16th. Just a few days from now, it will be 2 years of this flight. May 16th, 2010. Carried out by the shuttle Endeavour. AMS was 7.5 tons in weight, and the whole space shuttle weighs about 2,000 tons, mostly just fuel to carry the mission. The weather was not very good, but reasonably okay. It was all overcast of clouds, and so you get this very nice picture when the shuttle goes through the cloud, goes through right through the space. At about 2 minutes after the launch, the 2 solid rocket booster was burned out and separate from the shuttle. And in 3 days, in May 19th, the AMS was already installed. The AMS was installed on the space station truss. You see 2 astronauts here and here. 2 astronauts. So you see they're all painted white, including astronauts. I think it's for thermal management. I have a short video clip of the process. Sorry. This is the launch process of space shuttle. So So this, the launch was carried out. This is about 2 minutes. The rocket is going to be separated. See the 2 rockets separate from the shuttle itself. And then it continues for about 8 minutes, and then the external tank was thrown away. Now, in space, after the Columbia accident, the Columbia shuttle was damaged during the launch. the shuttle would have to fly behind the space station and make a flip, turn around for the astronaut on the space station to take a look around to see, make sure that there's nothing damaged during the launch. So that's the process. And then now we take the AMS by, on the flight day 4, AMS was ready to be installed. The first procedure is that the robot arm of the shuttle will first pick up AMS, take it away from the shuttle bay. And then there's another robot arm by the space station. It will pick up AMS and then take it to where it should be installed. So you see that the robot arm of space shuttle pick up AMS slowly, very slowly. Now it's away from the shuttle bay. The shuttle is here, the AMS is picked up. And now the robot arm from the space station come to pick it up. You see this is the robot arm come to mate with AMS. This is how they connect. And then the space station robot arm pick up AMS and eventually put it to the where it should mount. And in the meantime, you see the astronauts is preparing their spacesuit for the installation procedure. They get ready to go out. And Professor Samuel Ting talked to them to congratulate them for this work on AMS. I think that's all I want to show you. Yeah, there are many electronics behind it. In fact, this brings up the next slide, how we communicate with ground. AMS is basically run by itself. We don't actually need astronauts. Astronauts cannot, as I said, the astronauts cannot do the maintenance. The design of AMS does not allow them to access. So the data of AMS first goes through the system of electronic system in space station, and then it was sent to geosync satellite called TDRIS. This is used by the military. And then it brings down to the White Sand Ground Terminal in New Mexico, United States. And then on the ground, it's sent through just internet to first Marshall Space Center, where we have the media station, and then to CERN, where we have our payload control center. It's operating at CERN. So this whole procedure takes only a few seconds. We basically see the data immediately in real time. As soon as it's recorded by AMS detectors, it's going directly to our payload operation center, and then we can check the quality of the detector. So this is automated procedure. We don't really need astronaut. Astronaut keeps a backup system with a PC onboard International Space Station.
Is there a redundancy for data composition?
This system is actually placed as a redundancy. So the data will be transmitted and in the meantime recorded in this computer. Now, as soon as we verify the validity of the data on ground, we send a command and this computer will erase the data on top. And this computer can store, hold a long period, I think almost one week of data. And we have, and this is an old style notebook PC where you can slide in a hard disk to replace it. It's very easy to replace a hard disk. So in fact, we have stored many hard disks up there, just in case. But so far, the whole system works fine. So we've never been really need this system. The major challenge to operate a detector in space is the temperature environment or thermal environment in space. as you know, the space itself is at very low temperature. So the space is basically 3 degrees Kelvin. However, if it's face the sun, then the temperature can rise very fast because some gives a very big thermal power to the detector. How the sun radiates on AMS depends on where the space station is. The angle can vary from this, can go basically everywhere. So AMS doesn't have a fixed direction facing the sun. Every direction takes turn to become hot and cold. That's the main problem. In addition to the sun, space station radiates its heat via these radiators, white piece radiators. They radiate the heat generated by the space station. And this radiator sometimes face AMS, so the heat will come to AMS. And furthermore, the very big solar panel sometimes blocks the sunlight, sometimes reflects the sunlight to AMS. So the thermal environment is the biggest challenge, and it's really very complicated. As you can see, in this picture shows the temperature ecal. It can be as low as -10 degrees and sometimes as high as 30 degrees. And this on ground, this can be easily handled, but in space, this is really a challenge because we want to maintain a precision of about 10 microns in the mechanical accuracy of the detector. And you know that thermal expansion can easily destroy this precision. So we have put a lot of thermal sensors around the detector, hundreds of them all around the detector. But most importantly, the accuracy for these 9 layers of tracker has to be maintained down to about 10 microns. And the way we maintain this accuracy is that in the inner region, inside of the magnet, there's an active thermal control system where we actively bring the heat out or inject heat into it to keep a very constant temperature inside. So this picture shows the blue curve shows the temperature outside, as shown, that varies about 30 to 40 degrees. But inside, we can maintain the temperature. The red line is inner tracker. Inside the magnet, we can maintain the temperature down to about 1 degree. In space, this is really difficult because, as I said, there's no air. You cannot cool things with air. So everything has to be radiated. All the heat has to be radiated out. With this temperature control, we maintain an accuracy of the mechanical structure of tracker down to about 3 microns, 4 microns during the flight. This is about 1 year of time. So it was really kept quite constant. Now with this under control, I'll show some performance of the detector. This is our measurement of various ions in the cosmic ray. See, in cosmic ray, there are also all kinds of elements: lithium, beryllium, boron, carbon, nitrogen, and oxygen. And actually, this continues, but with much smaller quantity, up to iron, mostly. Above iron, we see very little ions. So with this, AMS can measure these ions very well. Now the key performance for us is the transition radiation detector. As I mentioned, we use this detector to separate electron from or positron from proton. Now this detector, the signal from this detector was used to build estimator. So this is a random scale. We just use this number to separate positron or electron from proton. And notice that this is a log scale, so actually this is very well separated. So we just separate them from here to here. And the performance is such that in the range from 1 GeV to about 1,000 GeV or a few hundred GeV, our proton rejection is better than 100, sometimes reaches 10 to the fourth. You see the drop here at about 400 or 500 GeV, the separation power becomes below 100 and eventually goes down to almost no power of rejection. This is because at this very high energy, proton behaves like the electron. It starts to radiate transition radiation as well. So you have no way to separate the proton from positron with this detector. But that's only at a very high energy. At lower than a few hundred GeV, we have very good separation. And I mentioned the other detector used to separate the positron from proton is this electromagnetic calorimeter. This is the momentum of an electron, and this is the proton rejection. As I mentioned, we were able to maintain a 10 to the 4 or better rejection up to very high energy. So this is the two primary detectors we use to reject the huge background from proton. So our experience of operating AMS in space station summarized two very simple statements that first, operating a particle physics experiment on the International Space Station is fundamentally different from operating an experiment in the LHC on ground. I think mainly because there's no maintenance and you have very limited resources like power and thermal control. But AMS is also different from a free fly satellite, for example, Hubble Space Telescope, because AMS is permanently attached with the International Space Station. Our direction, the direction of the detector is ultimately controlled by how the space station points. So we have no control of how AMS points in the space. And that creates the problem of thermal issue. So now let me switch to the measurement, positron to electron ratio. Let me first remind you where all the issue comes from, where the problem comes from. In cosmic ray, we know there are positron and electron. And the ratio was expected with showing this black curve. This is a conventional theory based on so-called diffused cosmic ray model. It assumes that cosmic ray all come from supernova explosion and then diffused through the space. If based on that model, we expect a declining ratio, positron flux over positron plus electron flux. The ratio of positron declines from 20% down to a few percent, 2%. And it was a very big surprise that Pamela in 2009 published a paper, give a measurement that actually rises above 10 GeV, goes up. And this, at that time, generates a lot of excitement because this indeed is an indication of some new physics beyond our traditional understanding of how cosmic ray is produced. And further experiment like Fermi, this is the green part is a Fermi experiment, confirms this trend, although the data is not really consistent, but there's a good indication that they go in the same direction. Now, this could be, people conjecture that there could be some reason for this. Now, to have a bigger, higher positron to electron ratio, what it implies is that there are some sources with higher positron ratio that is added to this diffused background, cosmic ray background. What can this be? This has to be a very high energy sources that maybe produce electron and positron in pair. So there are two models, basically one astrophysical source that's, for example, pulsar, very high energy photon can convert into positron and electron pair, and then you have more positron. So you need a nearby pulsar that gives us this rising. But it also can come from exotic source, for example, dark matter. That's how people start to think that this is related to dark matter, because dark matter annihilates if our space is full of this kind of dark matter particles, they annihilate and create electron-positron pairs. So you get the extra positron and you get a higher ratio. So these are possible models. These different lines shows possibly different dark matter mass of dark matter particles. It is really difficult to distinguish these two, so you need extra information. First of all, we need better measurements. As you see, the measurements are all scattered. You cannot really see very good how the trend is. And then in addition to this positron ratio, we probably have to include some other information like anisotropy or antiproton measurement, other ions, or gamma ray measurement. All these are topics that AMS is working on. But for now, first we measure the data, the E plus E minus ratio. We took first 18 months of operation. The data consists of 25 billion events, cosmic ray. That is, we register 25 billion event cosmic rays passing through the detector. Among them, about 6.8 million are electrons and positrons. Now this is the paper itself, but it also shows a typical event we register in this detector. I'll give you more details. So as I mentioned, this measurement, we first have a track measured by 1, 2, 3, 4, 5, 6, 7, 8, and 9 layers of tracker. This 9 layer of tracker forms a track, and we use it to separate electron from positron to tell the direction, whether it's a positive charge or negative charge. And then we have this measurement in transition radiation detector. The signal here indicates that it is electron or positron. And in the calorimeter at the bottom, the energy is very concentrated in the calorimeter, so it looks like electron and not a proton. Proton normally doesn't give you a very concentrated energy. So because of this shape of the electromagnetic shower down here, we can also tell that this is electron or positron. So this is the basic measurement that AMS is carried out. I can show you more pictures from 1 GeV. You see the same signature of event. 1 GeV electron and 1 GeV positron. About 10 GeV electron and positron. About 100 GeV electron and positron. And up to almost 1 TeV, 1000 GeV electron and positron. The measurement of AMS can reach about 1 TeV. That's the limit of our detector's precision. So above 1 TeV, probably events you can see the event, but you won't be able to tell what is the energy. So this also shows that the linearity or the measurement accuracy can reach from about GeV to TeV range. Now the principle of this measurement is that first we measure the electron by selecting charge -1 particle with an EM shower. So as I mentioned, that the energy in the electrocalorimeter should look very condensed and compact. That's an EM shower. So we choose a charge minus particle, and this part should looks like an electron. And for positron, certainly we select a charge +1 particle with EM shower. Now we have a huge proton background with 10 to the -4 ratio between E plus and proton. So this we require further separation power of PRD. As I will show you in this picture, this is already selected positive charged particle with EM shower, electromagnetic shower shape. And you see still about 1 to 1 in terms of number of proton and positron, 1 to 1. So before the EM shower separation, this part, the proton part, is about 10,000 times bigger. So it's a very huge background, but because of the EM shower, we have reduced it down to about 1 to 1. And then we use the transition radiation detector, TRD, to give further separation. This picture shows how they are separated in these two regions. And then you can very easily see if we cut here, we have a very pure positron sample and reject most of the proton. And that's how we get the pure positron ratio and how we measure the number of positrons to compare with the electrons. And another main issue is charge confusion due to scattering or secondary production from the electron. So this picture here, on top of the background from proton here, we also have a background from electrons. They are electron, so in TRD and electromagnetic calorimeter, they all look like electron, but the charge was measured wrong. It's electron, but we measure it as a positive charge particle. This is called charge confusion. This is because in the tracker, the particle may under scattering or produce secondary particle, and we are confused by the track. And these are reduced. How much this charge confusion contribute to the positron ratio can be estimated by Monte Carlo. This we cannot have estimation based on data. These are the Monte Carlo. The red line is a Monte Carlo curve of energy over momentum for electrons. Because electron has negative momentum, or negative means the charge is negative. So basically, all the measurements should be at -1. As you see, it actually peaks at -1. But there are a few of them actually comes to positive. So this part, we call it charge confusion. They are electron, but we measured it to a positive charge. And this red curve is from Monte Carlo, and the blue one is from data. And you see that Monte Carlo predicts very well the data, and this is positron part. So with this curve, we can estimate how much of this electron can mimic positron, and that creates the background. So with Monte Carlo, we can know, we estimated how much is this background from charge confusion, and it's typically about 10 to the minus 1% or below. At high energy, it can go up to about 10%, but it's manageable. So before we give the final results, there are many systematics errors that we have to estimate, including acceptance, asymmetry, selection dependence, migration, reference, spectrum, charge confusion. All this has to be studied in detail. This is also why it takes so long to publish a paper. There's many unknowns, and we have only cosmic ray itself to verify things. But I will not go into detail of this. It's quite tedious work. But finally, we publish a result which gives a table of, for example, here at energy 1.97 to 2.28 GeV, total 23,000 positrons. And the ratio of positron is 6%, 6.4%, with an error of 4.04%. So typically 1% error compared to the data, the result. And systematics 0.06%, also about 1%. Up to about 10 GeV to 30 GeV, the error is about 5%, 3 to 5%. And finally, our last measurement goes up to about 350 GeV. At 350 GeV, 260 to 350 GeV, we have only 72 events. And the error is about 10%, or above 10%. But the positron ratio goes up to 15%. Now, if we plot the data, we see a curve like this. At about below 10 GeV, it goes down to the minima, and then it continues rise. This is certainly in agreement with what Pamela has measured. And if I put AMS results with the previous measurements, you see several features. Let me first call your attention to this part at low energy. At low energy, here we see a discrepancy between AMS and the Pamela, but this is not a problem. This we understand. This is an effect called so-called solar modulation. It's related to the solar activities. The sun produce more or less solar wind. The solar wind can sweep away cosmic ray particles. So depends on the solar activities, we may have higher or lower ratio. But this is only for low energy particle. The high energy particle, the solar wind has no effect. So above 3 GeV, you see a perfect agreement between Pamela and the AMS. Up to about 100 GeV. Pamela's measurement stops at about 100 GeV, and we extend it to about 300 GeV. The second feature is that Fermi's result certainly is more or less ruled out. And third, more important, is that we see that this rising trend seems to come to a stop at the end. This is more clearly seen if I plot this in linear scale. You see that it goes up, rise up, and then it comes to a flat ratio. It doesn't really go down again, but this is a new feature compared to what Pamela and Fermi have shown. Now, this is certainly because we have a much extended energy range up to 300 GeV.
And that's also including the error bar also gets larger, right?
Yeah, certainly here, as I mentioned, this is about 10 to 15% of error bar. For them, yes, certainly at 100 GeV. This is not in disagreement, but for Fermi, you see the trend is sort of high. But I want to mention that Fermi has employed a really sophisticated method to measure the ratio, because in Fermi there's no magnetic field, so they have to use a very novel technology to separate positive and negative charge. They actually use the Earth magnetic field to do that. It's a really ingenious way of doing things. But unfortunately, this is really complicated. So it's expected that their measurements may be not so reliable. While Pamela and AMS both has its own magnetic field, pure Gauss order.
So the limit of resolution for AMS is 300?
This is 300 GeV. This is both for statistics. Mainly at this energy, it's statistics that limits the error. As I showed, at this point we have only 72 events in positron, and that's the main reason why we have a big error bar.
But what you do is the fact that energy gets so high, you can't basically split slightly the positron.
That's another reason. There are several reasons that we have to stop here at this moment, but this is subject to improvement. First reason is statistics. This point gets 72 events, so the next point is again probably about 20 events or so. So the measurement has too big error bar. Second reason is that the detector has some limits. As I shown that the TRD at about several hundred GeV, the TRD's efficiency separating positron from proton drops below 100 and even below 10. That's the second problem. And the third problem is that charge confusion start to go up. At this level, we have about 10%, but then it can be even bigger at a higher energy. So all these are technical issues that we have to overcome for the next measurement, for us to extend the measurements.
It shows some contrast in mentality. You knew the Pamela and the Fermi plot, but you chose to stop. You're showing the last two bins or something, which you could have, because you just want to compare.
Not really. But I mean, this point was at this moment the limit of measurements. I should say that there's no measurement above. There are no events also. Yeah, certainly. For example, if you the key problem of charge confusion is how well you can align the tracker. Now, to align the tracker, it takes a lot of detailed work because alignment of 9 layers of tracker separated by 3 meters, you want to align it to better than 10 microns is very difficult. And this is something that takes time and it will be improved continuously with our study. So yeah, up to about 300 GeV, we have about 10% charge confusion, but this can be, you already see from here that with 2 methods, we have already difficulty to come to a very good, consistent result. So for higher energy, at 1 TeV, this is yeah, but okay, these are things that we have to understand. But at the 10% level, this is the effect of this is not very big, and we can include it in the systematic errors. Certainly. This is the biggest challenge at TeV level. How well can we separate positive from negative charges?
Can you make it even longer? Is there money for that?
Well, it's probably no sense to discuss this now because it's impossible to do it. Even if we by design you can, but it's already out there. So
is there any chance of improving the second and third factor?
This we can certainly improve. We can certainly improve by more work. It's a continuous process to improve the alignment, improve the separation power, but it takes time. It's in progress. Okay, so as I mentioned, that this flatten out of the data, does it indicate that we are already at a plateau and start ready to go down the curve or not? I mean, we can really not, we don't really know. We have to wait for more statistics and more measurement for higher energy. So we are indeed very eager to see this next point. But so far we have seen up to 300 GeV. So finally, I give you a very simple interpretation of the data. This is done by experimentalists, so it has to be the simplest model that we can think of. We can construct a positron and electron flux, each by 2 factors. One is this conventional diffuse spectrum. So we have a positron part. It follows the power law of energy. So it goes as energy to the minus some gamma factor. Normally for electron, this is about energy to the minus 3. For positron, it's slightly stronger, energy to the minus 3.6. So this is a conventional part, diffuse the background. And then we assume there's a common source which produces E plus E minus in pairs. So you have the same power law and same constant with the cutoff. This cutoff corresponds to maybe the threshold, for example, the mass of the dark matter particle. It's an exponential cutoff with the power law spectrum. And now there are 7 parameters, but if we take the ratio, there are actually 5 parameters. So we fit it, and you get a very good fit. Actually, it's perfect. And the chi-squared divided by degree of freedom is even indicates that the fit is actually too good. But we draw some conclusion from this fit. For example, if we measure gamma E minus gamma E plus, minus 0.63. This indicates that the diffuse positron spectrum is less energetic, or it goes to the high energy, it goes down faster than electron. So this is, as I mentioned, this is roughly minus 3. Now the electron power factor compared to the common source, it's a positive. So it means that the source, the common source spectrum is more energetic, or stronger, harder than electron diffused background. The constant is the ratio of the relative number of particles. Positron to electron ratio in diffused particle is diffused spectrum is about 10%. This is more or less in agreement with the conventional model, but we have a common source which takes about 10 or 1%, 0.78% of the particle, the ratio. And this common source contributes to the rise of the spectrum. Finally, the cutoff is corresponds to about 760 GeV. This gives you an estimate of where the particle, if it's coming from an annihilation, how the annihilated particle, how heavy it is. If I take the residual, that is the data points minus the fitted curve, I get this. And you see that almost every point is within 1 standard deviation from the fit, from the data. So this gives us a hint that there's no structure. There's no structure in this distribution. All the fluctuation is probably just statistical fluctuation. Now I mentioned earlier that we want to. Oh, by the way, let me mention one thing. I said this model gives you some parameter, all this, but this doesn't really mean that we have already pinned down the source, the reason of this rise. You can actually invent many different models. All of them fit equally well. So this is just a very simple model. Turned out it fits well, but it doesn't give you any evidence that this is the truth. So the anisotropy, anisotropy means that the particle comes from a certain direction, or it prefers to come from one direction than the other direction. The way to do it is we measure the spectrum as a function of direction, and then we use this spectrum as a function of direction, and we expand it in spherical harmonica. And this shows how we do the spherical harmonica expansion, and then we measure the multiple of this expansion. The CL is this parameter. We add all the different m values to form this multiple direction. This is more or less an invariant independent from the coordinate system. And this gives you an indication of what is the size of the anisotropy in different multiples. This is, for example, dipole and quadrupole, etc., higher multiples. And these black dots are the measurement of this multiple CL. And this red curve is what we expect from a random distribution. That is a uniform distribution, but randomized, so that you have artificial multiple distribution. This is just a random spectrum. And you see our measurement is in agreement or even slightly lower than the random distribution, which says that our measurement doesn't show any meaningful anisotropy. So basically, we see an isotropic distribution of positron. There's no preferred direction. And we set a limit of 0.036 in terms of the cosine theta. That is the dipole part. The dipole part is very small, in agreement with 0. Okay, so this actually comes to the end of my talk. We have shown this data, and what we expect to see in a few years, or AMS expect to run 20 years in space. For the next 20 years, we hope that we can pin down problems and get a measurement here, which will give us a very clear indication of what's going on in this spectrum. So in conclusion, we have made a measurement on positron spectrum with 6.8 billion primary positrons and electrons. The positron ratio goes down or decrease for energy below 10 GeV. And above 10 GeV, from 10 to 250 GeV, the positron ratio goes up or increase steadily. And then the behavior of positron ratio from 250 to 300 GeV is now we need more data, but basically what we see is that it's a flat distribution, or the trend of increase seems to have stopped. Finally, the positron-electron ratio is consistent with isotropy, there's no direction. So we have a dipole component less than 0.036 with 95% confidence level. So this is the end of my talk. Thank you very much.
So very interesting talk. So now the floor is open for questions.
In this measurement, how long is the period? 2 years, huh?
18 months.
18 months.
1.5
So you
years.
assume there's no seasonal variation of the ratios, right?
We did check. We did check time variation of this measurement, but we don't see any significant variation.
So there are no, I see.
No.
Okay.
We checked, but because this number of events are limited by statistics, so we checked, for example, first half of 18 months and second half of 18 months.
Mhm.
The results are
But how about the low energy? Right now, it looks like you only check from 1 GeV up, right?
yeah,
And
low
there's
energy.
still a lot of events below 1 GeV.
At low energy, I should say I don't know. I think we do expect to see a variation due to solar modulation. So, but I didn't see the measurements.
You'll be interested to see that, I think.
Yeah.
Okay.
What is the statistics of the very last point, 350 GeV?
It's
Last year,
72 events in positron.
72 already.
Yeah, 72.
And the next one that you have not shown yet,
Yeah,
we're just trying to estimate how long it would take to
You
report
see
the next
the-
point.
You see how it goes down. So 134, 101, and 72. About. So you can see the estimation down.
So you don't have a curve to show what the number of events in terms of energy. But you show the,
No,
the
I-
diffraction, but not this number. This
This
plot,
is
right?
yeah. This is the number. What
So you could predict, I mean, how much time do you need to report the next set of data, right?
Yeah, I think indeed to make a sensible. You see the number is not small. In the next point, we probably will get some 30, 40 events already. But the measurement is some more difficult to do. Now in probably another 5, 6 years, we should have a few hundred events there.
Can you comment on the development of the systematic error? Because that's part of my earlier question. It's not just the
Yeah.
statistics, but whether
You see the systematics rise up very fast at the last 2-3 beams. That's exactly as I mentioned. The detector at that point has more uncertainty. TRD has a problem that above 400 GeV the protons start to radiate, and then the tracker. So to separate positive from negative charge, the tracker has also we have to do more work to pin down this problem.
So the red plot is total error.
The red part, this is the total error. Quadrature combined systematic and statistics.
Well, I have it. Let me ask one more question. Very early on, what was the fundamental reason for the magnet issue? Remind us now.
Okay.
Helium gas, yes.
The fundamentally we can come down to one issue, that is the lifetime of the helium. Because AMS, probably I should say from the beginning, AMS originally was designed with a superconducting magnet. This magnet was already built, and because in space, due to the limit in size and in weight, we cannot really bring a refrigerator up there. So we cannot create helium up there. We can only bring, so all the liquid helium for superconducting magnet has to be brought up with the detector. And it turned out, for some reason I cannot really say very clearly, it's also very difficult to feel superconducting helium through the detector because there's no gravity. It's difficult to feel. So you cannot refill the liquid helium. Now you bring up a certain amount of liquid helium and you can estimate how much time you get for the measurement, because the liquid helium just gradually burned out. And the estimation was too short compared to with superconducting magnet. The superconducting magnet has lower field with permanent magnet has lower field, but with much smaller acceptance, because we have to make the detector longer to compensate for the resolution. But still, at the end, the estimation says that it's better to have this permanent magnet running for a long time than a superconducting magnet running for a very short period.
The 18-year run is dictated by this smaller acceptance, right?
It's dictated by the lifetime of the space station.
Oh, okay. We even want to go longer.
Current estimation of how long the space station will work.
No, what I meant was saying if you really had the original projected superconducting magnet, you have larger acceptance, therefore you don't have to wait for ISS to expire. Right?
Yeah, sure. Yeah. But another factor is that the superconducting.
More question?
There's a question, but let me say a few words about this. It turned out the expire of shuttle flights is a factor. That originally AMS was supposed to go up and then come down after we run out of liquid helium, and possibly for the next flight. But because there's no space shuttle and the new vehicles that has been designed is not really powerful enough to carry AMS. So AMS goes up and it's really stuck there. There's no way you can take it down or repair it or do anything. So because that's another reason that we decided to eventually.
It looks like a improved version of Pamela may be able to compete with AMS at high energy band. So is there any proposal doing this?
I've never heard, I didn't hear anything from Pamela, but yeah, I should say no, I didn't hear anything.
The question from student. Okay, I have one question. So you show some component like carbon, etc. So these are number consistent with supernova exposure?
Yeah, oh, sorry.
In the very beginning. Some ratio or something.
Yeah, I think it's not, well, this measurement is has not been really calibrated. Now the number are just the number of events, but we didn't calculate the acceptance and everything. But having said that, you see this number, lithium, beryllium, boron, carbon, this trend is more or less inconsistent with what previous measurement, and also it's consistent with the amount of material on Earth. So from all they are both from supernova. So you see we have more carbon and then more oxygen. That's also on the Earth.
Okay, so let's thank the speaker. So,
Thank you.
I think we have the tea time in the 13th floor, so if you have some private question, you can still ask the professor.